The proposed method for environmental sound synthesis combines vocal imitations and sound event labels, utilizing a framework that consists of an encoder and a decoder. The encoder includes a feature extractor, which is pre-trained on environmental sounds, and a k-means clustering model. This setup allows for the control of pitch and rhythm in synthesized sounds, an improvement over conventional methods that only use sound event labels or images. The decoder follows the tachotron 2 model, and a neutral vocoder is used to synthesize the sound waveform from the predicted MEL spectrograms. In the experiments, vocal imitations were recorded for 31 sound event classes, with 3 males and 3 females acting as imitators. The model and learning configuration were set up with specific parameters, including the use of the Radom optimizer for training. Evaluations were conducted to assess the naturalness of the synthesized sounds, whether the synthesized sounds reflect the pitch and rhythm of the input vocal imitation, and whether the method follows changes in pitch and rhythm of vocal imitation. The results showed that the proposed method can synthesize high-quality sounds and provide controllability of the pitch and rhythm of synthesized sounds. The proposed method's ability to control the pitch and rhythm of synthesized sounds, as well as its overall impression, makes it a significant advancement in environmental sound synthesis. The proposed method of environmental sound synthesis from vocal imitations and sound event labels is evaluated through subjective and objective assessments. Tables 24 present the mean opinion score, MOS, and standard deviation of sound naturalness, pitch appropriateness, and rhythm appropriateness for each sound event class. The results show that the proposed method using vocal imitations and sound event labels scored slightly lower in overall sound naturalness than the method using only sound event labels. However, the proposed method provided higher sound naturalness for temporally sparse sounds, such as fireworks and door would knock, and equivalent naturalness to the reconstructed sounds for some sound events. The proposed method also showed higher appropriateness for pitch and rhythm of input vocal imitations compared to the method using only sound event labels. Figures 2 and 3 illustrate the MOS distributions and results of objective and subjective evaluations of sound control by pitch and rhythm change. The results demonstrate that the pitch and rhythm of the generated sound can be controlled by changing the pitch and rhythm of the input vocal imitation. However, changing the pitch and rhythm slightly degraded each MOS score, which will be investigated in future work. Figure 4 presents the results of objective and subjective evaluations of sound control by rhythm change, showing that the rhythm of the generated sound can be controlled by changing the rhythm of the input vocal imitation. Figure 5 displays the spectrograms of pitch and rhythm changed vocal imitations and synthesized sounds, confirming that the proposed method successfully reproduced the rhythm and pitch of vocal imitations. The limitations of this study include the low scores for intermittent sounds, such as engine, which will be analyzed further in future work. Additionally, the method's capability to control the synthesized sound by changing the pitch and rhythm of the input vocal imitation showed slight degradation in MOS scores. Future work will investigate these findings and explore combining additional information, such as images, to improve the method's performance. The paper explores the concept of generating audio scenes from visual onomatopoeic words, which are words that phonetically imitate, resemble or suggest the sound that it describes. This task is challenging due to the lack of large-scale datasets for audio scene synthesis. To address this issue, the authors propose a new dataset called Visual Onomato Wave, which consists of 5,000 audio clips and their corresponding visual onomatopoeic words. The proposed method utilizes a two-stage approach. First, it uses a pre-trained language model to generate a textual description of the audio scene based on the visual onomatopoeic word. Then, it employs a text-to-audio generation model to synthesize the audio signal from the generated textual description. The authors also introduce a new evaluation metric called Audio-Visual Onomatopoeic Similarity, AVOS, which measures the similarity between the generated audio and the target audio in terms of both auditory and visual aspects. The paper provides a comprehensive overview of existing datasets and techniques for audio scene synthesis, including AudioSet, FSD50K, and DiffSound. It also discusses various models such as SoundGen, Audio LDM, and BYOL Audio, highlighting their strengths and limitations in generating realistic audio scenes. Moreover, the paper presents a detailed analysis of the performance of the proposed method on the visual Okamoto wave dataset, demonstrating its effectiveness in synthesizing high-quality audio scenes from visual onomatopoeic words. The results show that the proposed approach outperforms state-of-the-art models in terms of both audio quality and relevance to the visual onomatopoeic words. In conclusion, the paper presents a novel approach to audio scene synthesis from visual onomatopoeic words, along with a new dataset and evaluation metric. The proposed method shows promising results in generating realistic audio scenes, paving the way for future research in this area.